Hi, welcome. I've been discussing about the spin-half system so far. However, the Stern galactic experiments can be performed on a variety of atoms or particles. Such experiments always results in a finite number of discrete beams coming out of the analyzer. For a spin-half system, there are two output beams, as we saw in the previous videos. For the case of three output beams, the deflections are consistent with magnetic moments arising from spin angular momentum components 1 h bar, 0 h bar, and minus 1 h bar. Along the z direction, the three output states are ket1 associated to this eigenvalue h bar, ket 0 associated to this 0 eigenvalue, and ket minus 1 associated to this eigenvalue minus h bar. This is the Spin-1 system. The three eigenvalue equations are, as before, let's keep the base of Z as the standard one. The eigenstates of Z can be written as follows. The matrix representation for the operator Z in its own basis is always diagonal, with the eigenvalues h bar, 0, and minus h bar along the diagonal. Therefore, Sz, the operator Sz, is represented by this following matrix in its own basis. Let's explore a little bit by looking at this Stern galactic experiment. If you perform this experiment, you will find 1/4 probability of finding ket 1, half probability of finding ket 0, and 1/4 probability of finding ket minus 1, and not 1/3 probability for each one, as you might expect. Based on that, we have these expressions for probabilities. Similarly, we can design another experiment considering the input state to be ket minus 1. So just as before, the probabilities are the same. There is no reason to believe that these probabilities here should be different. And based on the second experiment, we can have a set of equations for the probabilities involved in this experiment. Lastly, considering an input state ket 0, well, we don't need to perform any experiment to know the probabilities. Intuitively, it can be determined based on the two performed experiments. There are three probabilities involved for the input state ket 0, and they are: what results should we expect? Previously, we had this probability of finding ket 0 if an input state is ket 1, given by this expression. And this expression was equals half. Mathematically speaking, we know that if we have this inner product, the same inner product we have here, it equals minus Bra-1 ket 0 subscript x. But in this case here, This inner product is inside this module squared, which doesn't matter if you have this minus sign here or not. And then we can interpret that this first probability here is also equals half for this property here. If this probability is equals half, this probability for the input state ket 0 also must be half. Similarly, for the other case, then this last probability here must be half either. Then, as we know that the sum of all the probabilities must be equals 1, there is no doubt that this probability in the middle must be 0. Now that we have all the probabilities involved for the 3 input states, we are ready to find out who ket 1 subscript x, ket 0 subscript x, and ket minus 1 subscript x are in terms of the eigenstates of SZ. Let's assume these general kets as working on the first expression, alpha 1, we can determine the coefficients a, b, and c. We can use the expressions for the probabilities found previously to determine these coefficients. So if you calculate this inner product right here, considering this quantum state ket 1 subscript x, and take the module squared of it and set it equal to 1/4, you will end up with a equals 1/2. The same for the other input states. Therefore, in principle, our ket 1 subscript x will be half ket 1 plus 1 over square root of 2 ket 0 plus half ket minus 1. I just plug back the value for the coefficients a, b, c into this equation alpha 1. Now, similarly, I work on the expression alpha 2 and using the probabilities involved with the ket 0 subscript x found before, and the same for the expression alpha 3 using the probabilities which are involved with this quantum state ket minus 1 subscript x. Now is the trick. If you look at these two expressions, you will see that they are the same. But they cannot be the same since they represent different input states. What we can do then? The overall phase of a quantum state vector is physically meaningless. Only the relative phase between different components of the state vector is physically measurable. Hence, we're free to choose one coefficient of each vector to be real and positive, without loss of generality. Following the convention, I'll insert the relative phase on the ket 0, ket minus 1, and ket 0 right here. It will be something like exponential I alpha, exponential I gamma, exponential I beta. We need to determine alpha, gamma, and beta now. To find a relationship between alpha and beta, I'll use the fact that these cats, cat T1 subscript x and the cat minus subscript x, are orthogonal. And then, mathematically speaking, it means this inner product is equals 0. Let's perform this calculation and find the relationship between alpha and beta. In order to have these two input states being orthogonal to each other, alpha and beta must follow this relationship right here. The natural choice would be alpha equals beta equals 0. If we make this choice, we end up with these are the two quantum states for the cat 1 subscript x and cat minus 1 subscript x, and you can check by yourself. If we calculate the inner product between these two input states, you end up with 0, as it should be. Now we just need to determine gamma. For that, I'll calculate the following inner product. Finally, these are the three eigenstates of the operator Sx written in the basis of Sz for the Spin-1 system. Following similar ideas, you can find the eigenstates of the operator Sy in the Sz basis for the Spin-1 system. This is all for this video. Thanks for watching. Bye for now.